December 7, 1941. Pearl Harbor burns, and within 72 hours the United States military faces a logistics nightmare that has nothing to do with battleships or aircraft. Across the Pacific Theater, from the Philippines to Wake Island, American forces are sleeping in canvas tents that disintegrate under tropical downpours within 3 weeks. The War Department's morning briefings turn grim when field reports arrive describing entire supply depots flooded, ammunition ruined, and soldiers hospitalized with pneumonia because their shelter literally fell apart during monsoon season. Traditional wooden barracks require skilled carpenters, weeks of construction time, and lumber that simply doesn't exist on remote coral atolls. The Navy calculates it would take 18 months to build conventional housing for the forces they need to deploy immediately. In Washington, Brigadier General Eugene Raybould stands before a crisis table covered in weather maps and construction timelines. His engineers present the impossible equation. They need structures that can be manufactured in Pennsylvania, shipped 10,000 miles through submarine-infested waters, assembled by exhausted Marines who've never held a wrench, and survive everything the Pacific can throw at them: 130-degree heat, Category 5 typhoons, monsoons that dump 15 inches of rain in 6 hours, and the very real possibility of Japanese bombing runs. The standard Army tent costs $12 but lasts 1 month in jungle conditions. A wooden barracks building costs $8,000 and requires a construction crew for 6 weeks. Neither option works when you're island hopping across the Pacific and need shelter for 50,000 men yesterday. The British have been fighting longer, and their experience in North Africa offers a clue. Since 1916, they've used Nissen huts, semicircular steel shelters invented by Canadian engineer Peter Nissen during World War I. These corrugated iron half-cylinders house 30 soldiers, require no skilled labor to erect, and laugh at sandstorms. But the Nissen design has critical flaws for Pacific deployment. The British version uses heavy steel panels that need specialized lifting equipment. The ventilation system works for the Libyan desert, but turns the interior into a steam cooker in Philippine humidity. Most damaging, each hut requires custom foundation work, which means pouring concrete or building wooden platforms, which brings you right back to the carpenter problem. Raybould's team calculates they need shelter for 2 million personnel across hundreds of islands and bases. The math is brutal. At conventional construction rates, the war would be over before half the troops had roofs. Soldiers are already writing letters home, describing how they wake up with their boots full of rainwater, how fungus grows on their uniforms overnight, how the temporary tents collapse during storms and send men scrambling in the mud at 0300 hours. The Medical Corps reports that respiratory infections are hospitalizing more men than enemy action in some sectors. This isn't just about comfort. It's about maintaining a fighting force that doesn't rot away before seeing combat. The call goes out to American engineering firms, university research departments, and the Navy's own construction battalions. The specifications sound like science fiction. Design a building that weighs less than a Jeep, fits on a single rail car, requires no foundation, assembles in 1 day with basic tools, costs less than $1,000, and survives conditions that destroy permanent buildings. Oh, and have 10,000 units ready to ship in 6 months. It's February 1942, and somewhere in Rhode Island, a team of engineers is about to turn architectural impossibility into reality. The Nissen hut blueprint arrives at the Navy's Bureau of Yards and Docks in a peculiar twist of wartime cooperation. British engineers, grateful for American supply shipments, share detailed technical drawings of their World War I shelter design, 16-foot wide semicircular tunnels made from corrugated iron sheets bolted to a wooden frame. Commander John Philip Drostfeld studies the specifications and immediately sees both genius and problems. The genius, the arch shape, naturally deflects wind and sheds water without complex engineering. The problems, a laundry list that would doom the design in Pacific conditions. The British huts weigh 3 tons when disassembled, require foundation bolts drilled into concrete, and use an internal wooden frame that becomes a feast for termites in tropical climates. Drostfeld circles the ventilation specs in red ink. 2 small windows designed for Scottish weather would turn these things into ovens at Guadalcanal's 98-degree average temperature. But there's another American voice in this conversation, and it comes from an unexpected corner. Buckminster Fuller has been preaching prefabricated housing since the 1920s, though most architects dismiss him as a crank. His Dymaxion house concept, factory-built, lightweight, assembled on site, reads like prophecy in 1942. Fuller's ideas about mass-producing housing like automobiles, using industrial materials instead of traditional lumber, and designing for rapid deployment all sound less crazy when your country needs to build an entire city's worth of shelter every month. The military hasn't directly consulted Fuller, but his published papers circulate through engineering departments, and his core insight proves invaluable. Treat buildings like manufactured products, not construction projects. The Navy consolidates this thinking at their facility in Quonset Point, Rhode Island, a freshly commissioned air station on Narragansett Bay. The location isn't random. Rhode Island has deep manufacturing expertise in sheet metal from its jewelry and silverware industries, plus proximity to steel mills in Pennsylvania and shipyards that understand marine-grade corrosion resistance. In March 1942, the Navy assembles an unusual team, structural engineers from the Strand Steel Corporation who've been building prefab farm buildings, architects from George A. Fuller Construction Company who specialize in rapid assembly methods, and Navy officers who've actually served in the Pacific and know what typhoon-proof really means versus what it means on paper. The team lead, Otto Brandenberger, brings farm-building experience that turns out to be exactly right for this problem. His strand steel barns use self-supporting arched panels, no internal frame needed, which means no wood for termites to eat and no complex joinery to fail during storms. Brandenberger's radical proposal: eliminate the Nissen hut's wooden skeleton entirely and make the corrugated steel skin carry all the loads. This violates conventional architectural wisdom in 1942, where steel is for bridges and skyscrapers, not self-supporting buildings. But Brandenberger knows his barns have survived Midwest tornadoes without internal framing, and he's willing to bet the same principle scales up. The British contribute another crucial element through their painful experience. Their Nissen huts in Burma and Singapore have taught them exactly how tropical environments destroy buildings. Fungus isn't just cosmetic. It literally eats through wood preservatives and paint within months. Humidity doesn't just make things damp, it corrodes metal fasteners until roofs collapse. Insects aren't merely annoying. Carpenter ants can reduce wooden support beams to hollow shells in one season. The British reports read like horror stories, but they provide the Quonset team with a checklist of everything that must be engineered out of the design from day one. No wood in contact with ground. All steel hot-dip galvanized, not just painted. Ventilation aggressive enough to prevent condensation. Every fastener accessible for replacement without disassembling the structure. By April 1942, the hybrid vision crystallizes. Take the Nissen hut's brilliant arch geometry, strip out everything that makes it heavy or vulnerable, add Fuller's mass production philosophy and American steel manufacturing muscle, then engineer every detail for the specific hell of Pacific Island warfare. April 15, 1942. Otto Brandenberger walks into a Quonset Point warehouse with 30 engineers and a deadline that would be laughable if the war situation weren't so desperate. 60 days to design, prototype, test, and approve a completely new building system that doesn't yet exist. The team works in shifts around the clock, sleeping on cots pushed against the warehouse walls, subsisting on Navy mess hall coffee, and the kind of pressure that either produces brilliance or complete collapse. Brandenburger divides his crew into specialist teams. One group tackles aerodynamics and structural loading, another figures out how to nest components for shipping, a third works exclusively on the joint and fastener problem that plagued the British design. The first radical decision happens on day 3. Traditional architectural drawings take weeks to produce, and the team doesn't have weeks. Instead, they build in real time, sketch a detail in the morning, have the metalworking shop fabricate it by afternoon, test it overnight, and revise by dawn. This iterative prototyping approach is standard in 2025, but revolutionary in 1942 when buildings are designed completely on paper before a single piece is cut. The warehouse floor becomes a laboratory scattered with failed joint experiments, bent test panels, and increasingly refined versions of each component. The engineers steal a technique from aircraft manufacturing. Every part gets a number, every revision gets documented, and nothing moves to the next prototype generation without solving the previous version's failure points. The dimensions come from brutal practicality rather than aesthetic choice. 16 feet wide, the maximum that fits on a standard railcar without special permits. 20 feet long per section, short enough that 4 men can lift a panel, but long enough to create usable interior space. 48 feet total length when assembled, housing capacity for 36 men with bunks, or converting to office space, medical stations, or supply storage. The Quonset team discovers that this size hits a sweet spot in structural engineering. Make it smaller, and you waste shipping capacity. Make it larger, and the panels become too heavy for field assembly, or the arch starts requiring internal supports that reintroduce all the problems they're trying to eliminate. The arch radius calculation consumes 2 full weeks of the 60-day deadline. 2 flat and wind forces could peel the structure like a sardine can. Too steep and you waste interior headroom and create difficult end wall geometry. Brandenburger's team settles on an 8-foot radius, a perfect semicircle that provides 7-foot headroom at the sides and creates what structural engineers call a self-bracing arch. The corrugated steel naturally wants to hold this curve, which means the panels can be thinner and lighter than flat sheets would require for the same strength. They run load calculations showing this design can theoretically handle snow loads up to 40 pounds per square foot and wind speeds exceeding 100 miles per hour. But theoretical calculations and Pacific typhoons are different animals. By day 40, they have something that looks like it might work. A Frankenstein's monster of riveted panels, experimental joints, and borrowed hardware. The first complete prototype goes up on May 25, 1942, assembled by 6 sailors who've been given 4 hours of instruction and basic hand tools. The assembly time, 14 hours, which is encouraging but not yet good enough. The Navy wants single-day construction capability because marine landing schedules don't allow for multi-day building projects. The team identifies the bottleneck immediately, the floor system. They've been trying to include a wooden floor as part of the package, but it's the slowest part to assemble and the first thing to rot in tropical conditions anyway. The solution is elegant in its simplicity. Eliminate the floor entirely from the basic design. The hut sits directly on whatever surface exists, coral, sand, dirt, or if you're lucky, gravel. For applications requiring finished floors, those can be added later as a separate project, but the basic shelter achieves weather protection without them. This single decision cuts assembly time to 8 hours and reduces shipping weight by 1,200 pounds per unit. On June 10, 1942, the final prototype stands complete. 96 corrugated steel panels, each weighing less than 50 pounds, that bolt together to create 720 square feet of enclosed space. Total materials cost $1,394. Total weight 9,000 pounds. The real test begins when the Quonset prototype faces the engineering equivalent of an interrogation. Navy structural engineers arrive with wind load tables, typhoon data from meteorological stations across the Pacific, and a healthy skepticism that this corrugated tunnel can survive what nature throws at tropical islands. The numbers they're working with aren't theoretical, they're pulled from actual weather events. Typhoon Gloria hit Guam in November 1940 with sustained winds of 140 miles per hour and gusts reaching 180. The 1935 Labor Day hurricane that killed 400 people in the Florida Keys produced winds so powerful they sandblasted paint-off buildings and drove wooden planks through palm trees like spears. If Quonset huts fail in a storm, the result isn't just property damage, it's dead servicemen and destroyed equipment. Brandenburger's team starts with the fundamental physics of why the arch shape works. When wind hits a flat wall, it creates what engineers call a pressure coefficient. The wind pushes directly against the surface with maximum force. But a curved surface deflects wind upward and around, reducing that pressure dramatically. Think of how water flows around a river stone versus slamming into a dam wall. The semicircular Quonset profile means hurricane-force winds slide over the structure rather than trying to punch through it. The corrugations add a second layer of brilliance. Those ridges running lengthwise create structural rigidity, the way folding a piece of paper makes it stronger than leaving it flat. Each corrugation acts like a tiny I-beam, resisting bending forces that would crumple smooth sheet metal. The math gets fascinating when you examine how loads distribute through the arch. In a conventional rectangular building, the roof pushes down on walls, the walls push down on foundations, and everything depends on those vertical load paths staying intact. Storm winds can literally lift roofs off because they're separate elements just sitting on top of walls. The Quonset arch changes this completely. It's a single continuous curve where every panel shares the load with its neighbors. Engineers call this a compression ring, and it's the same principle that keeps stone bridges standing for centuries without mortar. The hoop stress, the tension trying to spread the arch apart at its base, gets resolved by the ground itself. Each Quonset panel is bolted to the adjacent panel with 3/4-inch steel bolts spaced every 6 inches, creating what's essentially a 48-foot-long steel cable wrapped in an arch shape. But theoretical strength means nothing without testing, so the Navy sets up validation experiments that border on sadistic. They build a full-scale Quonset at Davisville, Rhode Island, and instrument it with strain gauges, pressure sensors, and deflection meters. Then they wait for the first major nor'easter. On March 3, 1943, a storm hits with 75-mile-per-hour winds and heavy snow loading, perfect test conditions. The instruments record the structure flexing by less than 2 inches at the crown, then returning to its original shape when the wind subsides. The panel joints hold, nothing leaks. The structure behaves exactly as the calculations predicted, which is both thrilling and slightly terrifying, because it means they're about to bet thousands of lives on this design. The tropical environment testing proves more challenging than wind loads. You can't simulate years of jungle conditions in a Rhode Island warehouse, so the Navy ships a test unit to the Panama Canal Zone where humidity averages 85% year-round and temperatures stay above 80 degrees. 6 months later, the report comes back. Minimal corrosion on the galvanized panels, no structural degradation, but serious problems with interior condensation. When hot, humid air hits the relatively cooler steel at night, water literally rains from the ceiling inside the hut. The solution requires adding ventilation louvers at both ends and along the ridgeline, openings that let hot air escape and create airflow without compromising structural strength or weather protection. These vents add $47 to the unit cost, but transform the hut from a steel sauna into something humans can actually occupy in tropical heat. The final engineering challenge is the foundation question. How do you anchor a 9,000-pound building to loose sand or coral without pouring concrete? The answer comes from tent technology scaled up, steel stakes driven into the ground, connected to the hut's base with adjustable tension cables. For harder surfaces, the team designs a bolt pattern that lets the hut mount directly to wooden sleepers or pierced steel planking. The beauty of this system is its forgiveness. The structure can flex slightly with ground movement without tearing itself apart. June 1942. The War Production Board approves Quonset hut manufacturing, and what happens next is American industrial capacity operating at its absolute peak. The Navy contracts with 10 major steel fabricators across the Midwest and Northeast, companies that were making grain silos and water tanks 6 months ago and are now retooling for military shelter production. The Strand Steel Corporation converts its entire Penrose facility outside Philadelphia to exclusive Quonset production. George A. Fuller Construction takes over a former automobile parts plant in Chicago. Great Lakes Steel dedicates 2 rolling mills to nothing but corrugated panel production. By August, these factories are collectively producing 1,500 complete huts per week, and the number keeps climbing. The manufacturing process borrows heavily from automotive assembly line logic. Massive steel coils arrive by rail. Each coil is 4 feet wide and contains enough steel for 30 panels. Rolling machines corrugate the flat steel, creating those structural ridges at precisely 2.67 inches on center. The corrugating process work hardens the steel, making it stronger than the flat sheet that went in. Next, the panels go through galvanizing tanks where they're dipped in molten zinc at 850 degrees Fahrenheit. This zinc coating isn't paint. It's a metallurgical bond that sacrifices itself to corrosion before the underlying steel can rust. In Pacific saltwater air, this galvanizing means the difference between 5-year lifespan and 50-year lifespan. The process costs an extra $112 per hut, but proves non-negotiable after field reports show ungalvanized steel corroding through in 8 months. Each complete hut kit gets packaged with obsessive attention to shipping logistics. The 96 corrugated panels nest inside each other like stacked bowls, reducing the package height from 8 feet to just 14 inches. The end walls, plywood sheets with pre-cut door and window openings, pack flat between the steel panels. All fasteners, bolts, and hardware get boxed in a single wooden crate that includes illustrated assembly instructions designed for men who might not read English fluently. The entire kit loads onto one standard flatbed railcar measuring 40 feet long. This packaging density is crucial because every train heading to West Coast ports is carrying either Quonset huts, ammunition, food, or vehicles. There's zero room for inefficient cargo. The shipping choreography gets wild. Trains leave Philadelphia and Chicago daily, arriving at San Francisco, San Diego, and Seattle, where Liberty ships and specialized cargo vessels wait at dock. Longshoremen load complete huts into shipholds using the same crane systems designed for tanks and artillery. A single Liberty ship can carry 200 Quonset huts, plus their assembly hardware, representing shelter for 7,200 men. The War Shipping Administration tracks every cargo manifest because these aren't just buildings, they're strategic assets. A hut that ships to Guadalcanal in September might house a bomber crew by October, making the difference between operational aircraft and pilots sleeping in mud. The assembly process on the receiving end is where Quonset design genius really shines. The Navy's construction battalions, the famous Seabees, develop standardized procedures that turn shelter erection into a choreographed operation. 6-man crew, 8 hours, 1 complete hut ready for occupation. The process starts with site preparation. Level the ground, remove vegetation, lay down a gravel base if available. 2 men handle the end walls while 4 wrestle the steel panels. The panels overlap by 6 inches and bolt together with those 3/4-inch fasteners. No welding required, no concrete needed, no skilled trades necessary. Just wrenches, a level, and men who follow the illustrated instructions. The speed record gets set on Espiritu Santo in January 1943, when a specially trained CB crew erects a complete hut in 4 hours and 17 minutes. But that's showboating. The real achievement is sustained production across hundreds of islands where crews throw up 5 or 6 huts per day, day after day, building entire bases faster than the Japanese can bomb them back to rubble. By December 1943, monthly production hits 8,000 units. The logistics network moves so efficiently that huts ordered in Pennsylvania reach New Guinea within 40 days, including ocean crossing and trans-Pacific transport. The cost accounting tells the victory story. Each Quonset hut provides 36 men with weatherproof shelter for $1,394 in materials and approximately 60 man-hours of assembly labor. Compare this to conventional barracks, $12,000 in materials, 400 man-hours of skilled carpentry, and 6 weeks construction time. The Quonset delivers shelter at 1/10 the cost in 1/20 the time. By mid-1944, the U.S. military has deployed over 160,000 units to every combat theater. That's housing capacity for nearly 6 million personnel, built in less than 2 years. Guadalcanal, August 1942. The first combat-deployed Quonset huts arrive on a beach where the temperature hovers at 95 degrees with 90% humidity, and Japanese bombers make daily visits to crater anything that looks like American infrastructure. Marine engineers unload the flat-packed steel panels under sporadic artillery fire and start bolting them together in a coconut grove, still showing scorch marks from the previous week's shelling. Within 12 hours, Henderson Field has 10 new structures housing maintenance crews for the battered F-4F Wildcats operating from the airstrip. The real test comes 3 days later when a Japanese bombing run scores a near miss. A 500-pound bomb detonates 40 yards from a hut full of aviation mechanics. The blast wave flattens surrounding palm trees and shreds canvas tents like tissue paper, but the Quonset flexes, dirt and shrapnel rattle off the corrugated steel, and when the smoke clears, the structure stands intact with every man inside, shaken but alive. The jungle environment proves as hostile as enemy action. Within 2 weeks, red rust streaks appear on any ungalvanized fasteners. The salt air eats through standard hardware like acid. Fungus grows on everything that holds moisture, turning the inside surfaces into abstract art exhibits of black and green mold. The ventilation louvers that seemed adequate in Rhode Island testing barely move the suffocating air. Marines start propping doors open 24/7 and cutting additional vent holes with tin snips, violating structural specifications but making the huts livable. These field modifications get documented and sent back to Quonset Point, where engineers incorporate them into later production runs. More ventilation, larger louvers, and every single fastener galvanized regardless of location. Iwo Jima, February 1945. The volcanic island offers a different kind of hell. Black sand that blows into every crevice, no topsoil for grounding stakes, and the constant threat of artillery from Mount Suribachi. Seabees arrive on D-Day +2 and start assembling Quonset huts under fire, literally bolting panels together while mortar rounds impact 200 yards away. The volcanic sand proves impossible for traditional stake anchoring, so crews improvise by filling empty oil drums with sand and cables connecting drums to the hut bases. When a Pacific typhoon hits in March with 110-mile-per-hour winds, those improvised anchors hold while wooden structures across the island disintegrate. The base commander's report back to Pearl Harbor is succinct. Quonset huts survived. Everything else gone. The Arctic environment tests the design from the opposite extreme. Alaska's Aleutian Islands campaign sees Quonset huts deployed at Dutch Harbor and Adak, where temperatures plunge to -40 and winds regularly exceed 100 miles per hour. The cold makes the steel brittle, and early units suffer from panels cracking at the bolt holes. Engineers respond by specifying cold-rolled steel with different metallurgy for Arctic deployments and adding rubber gaskets at every joint to maintain flexibility. Heating the huts creates its own problems. Warm air meeting frozen steel produces condensation that literally rains inside until crews learn to install insulation blankets and run ventilation, even in sub-zero weather. By winter 1943, weatherized Quonset models include internal insulation batting, double-wall construction for extreme cold zones, and modified ventilation systems that prevent heat loss while managing moisture. North Africa and Italy bring different challenges entirely. At Palermo, Sicily, a Quonset hut pressed into service as an ammunition depot takes a direct hit from a German 88mm artillery shell. The shell penetrates the steel skin, detonates inside among crates of small arms ammunition, and the resulting explosion should theoretically vaporize the structure. Instead, the arched shape channels the blast force outward through the walls and roof in a pattern that leaves the structural frame twisted but standing. EOD crews examining the wreckage note that a rectangular building would have collapsed completely, trapping anyone nearby under tons of rubble. The arch's inherent strength, that compression ring effect, means even catastrophic damage doesn't trigger total structural failure. The Pacific typhoon season of 1944 delivers the ultimate stress test. Super Typhoon Cobra hits the Philippines in December with winds measured at 140 miles per hour and 20-foot storm surge. At Tacloban, the storm destroys 80% of all structures on the base. Wooden buildings explode into splinters. Concrete block structures collapse when wind undermines their foundations. But of 43 Quonset huts on the base, 39 survive intact and 4 suffer repairable damage, bent panels and torn seams, but no total failures. Engineers analyzing the survivors find that proper anchoring matters more than any other factor. Huts with adequate ground attachment ride out the storm, those with improvised or insufficient anchoring roll like tumbleweeds. By war's end, field performance data from 50 combat zones feeds back into continuous design improvement. The 1945 production models bear little resemblance to the 1942 prototypes. Better ventilation, stronger fasteners, improved insulation options, and field-tested modifications that turn a good design into an exceptional one. May 8, 1945, victory in Europe. August 15, 1945, victory over Japan. Suddenly, the United States military owns roughly 170,000 Quonset huts scattered across 6 continents and has absolutely no idea what to do with them. The original plan assumed these were temporary wartime expedients that would be scrapped or abandoned once permanent facilities could be built. But something unexpected happens. Nobody wants to get rid of them. At hundreds of military bases slated for closure or downsizing, commanders look at their Quonset huts and see not obsolete wartime relics, but perfectly functional buildings that cost nothing to maintain and can be repurposed for virtually anything. The War Assets Administration, tasked with liquidating surplus military property, finds itself facing an unusual problem. There's more demand for used Quonset huts than they have inventory to sell. Veterans returning home discover a housing shortage so severe that families are living in converted chicken coops and sharing apartments with 3 other families. The construction industry, starved of materials and labor during 4 years of war, can't build fast enough to meet demand. Into this crisis steps the Quonset hut, now available for civilian purchase at liquidation prices, $1,000 to $2,500 for a complete structure that would cost $8,000 to build conventionally if you could even find contractors available to build it. The federal government actively encourages this repurposing through programs that prioritize veterans for Quonset purchases. By late 1946, Suburban developments made entirely of Quonset huts spring up around every major city. Roger Young Village in Los Angeles houses 750 families in converted military huts. Vetville developments appear near universities where the GI Bill is flooding campuses with students who need immediate housing. The architectural adaptation gets creative fast. Families add wooden facades to the curved ends, making the structures look less like military surplus and more like quirky cottages. Interior walls divide the open space into bedrooms, living areas, and kitchens. Windows get cut into the steel sides, violating every structural principle but making the spaces actually livable for family life. Some owners go further, burying the entire structure halfway into the ground for earth-sheltered insulation or connecting multiple huts end to end to create sprawling compound homes. Housing inspectors and building code officials initially balk at approving these modifications, but the housing shortage is so desperate that municipalities reluctantly grant permits. In Portland, Oregon, an entire neighborhood called Fairview Addition consists of 350 Quonset homes. Residents plant gardens, paint their steel walls cheerful colors, and build conventional-looking porches that disguise the utilitarian origins. Churches discover Quonset huts solve a different problem, providing worship space for exploding suburban populations without the decade-long capital campaigns traditional church buildings require. First Presbyterian Church of Levittown, Pennsylvania, holds services in a Quonset hut from 1952 until 1967, when they finally raise funds for a conventional sanctuary. Dozens of congregations make the same calculation. $2,500 for immediate space beats $150,000 for eventual grandeur. The acoustics are terrible, the aesthetics underwhelming, but people can gather for worship next month instead of next decade. Some of these temporary church huts remain in service for 30 years, outlasting the generations who first considered them stopgap solutions. Education sees similar adoption. Post-war school enrollment explodes as the baby boom hits, and school districts face the same impossible math that plagued the military in 1942. They need classrooms immediately, and conventionally built schools take years to construct. Rural districts especially embrace Quonset classrooms. A single hut provides space for 30 students at 1/10 the cost of traditional construction. By 1950, an estimated 3,000 schools across the United States include at least one Quonset hut classroom. Some students spend their entire elementary education in these steel tunnels, learning multiplication tables and history lessons under curved ceilings that once sheltered B-29 crews in the Pacific. The commercial sector joins the party. Small businesses, machine shops, auto repair garages, warehouses, farm equipment storage recognize that Quonset huts deliver clear span space without internal support columns, making them perfect for industrial work. A welder can set up shop in a surplus hut for less than 2 months' rent in conventional commercial space. Agricultural use proves especially popular. The original Strand Steel Corporation, having helped design military Quonsets, returns to manufacturing civilian versions specifically marketed to farmers. Thousands of Midwestern farms add Quonset storage buildings for grain, equipment, and livestock shelter. The maintenance requirements are minimal. Hose off the exterior once a year, check the bolts occasionally, and the structure lasts indefinitely. This civilian adoption creates an accidental architectural legacy. Quonset huts become embedded in American visual culture as symbols of practicality over pretense, function over form, and making-do ingenuity. They appear in movies, television shows, and photographs as shorthand for post-war optimism mixed with austerity. Architectural historians initially dismissed them as temporary eyesores, but by the 1990s, preservationists start recognizing surviving Quonset huts as important examples of adaptive reuse and vernacular architecture. Several achieve historic landmark status, protected as representing a unique moment when military technology successfully transitioned to civilian life. Modern disaster zones tell you everything about why the Quonset hut's DNA keeps reappearing in 21st century emergency response. When the 2010 Haiti earthquake destroys Port-au-Prince, relief organizations face the same equation American military planners confronted in 1942: immediate shelter for hundreds of thousands of displaced people, no existing infrastructure, no time for conventional construction, and conditions that destroy inadequate temporary housing within months. The solution that emerges borrows directly from Quonset principles even when designers don't realize they're channeling 1940s military engineering. Arched steel frames, corrugated metal panels, prefabricated components that ship flat and assemble quickly. The basic formula hasn't changed because the underlying physics and logistics haven't changed. The United Nations High Commissioner for Refugees currently uses shelter systems called RHUs, refugee housing units, that are essentially Quonset huts with 80 years of materials science improvements. Instead of corrugated steel, they use insulated composite panels. Instead of bolt-together assembly, they employ snap-fit connections. But the core concept remains identical: curved profile for structural efficiency and wind resistance, self-supporting arch, eliminating internal framing, flat-pack shipping, allowing massive quantities to reach remote locations, and assembly by unskilled labor with minimal tools. A two-person crew can erect a modern RHU in 4 hours, almost exactly matching the 1942 Quonset specifications. These units currently house over 200,000 displaced persons in refugee camps across Africa, the Middle East, and Asia. Hurricane-resistant construction has rediscovered arch geometry after decades of building conventional rectangular structures that hurricanes repeatedly destroy. After Hurricane Katrina devastated the Gulf Coast in 2005, engineers studying which buildings survived found that curved structures consistently outperformed rectangular ones. The Mississippi coast saw entire neighborhoods of conventional homes reduced to foundation slabs, while a handful of Quonset-style metal buildings stood intact with minor damage. This empirical evidence triggered research into what structural engineers call aerodynamic architecture, designing buildings that work with wind forces rather than resisting them through brute strength. The result looks remarkably like a Quonset hut because the physics haven't changed. Wind flowing over a curve creates less pressure than wind slamming into a flat surface, today exactly as it did in 1942. The modern tiny house movement unknowingly reinvents Quonset principles when designers seek maximum interior space with minimum materials and cost. Several companies now manufacture arch-roofed prefab cabins using the same corrugated metal and self-supporting curve that Otto Brandenburger pioneered. These sell to buyers seeking affordable housing, disaster-resilient structures, or off-grid living solutions. The marketing emphasizes sustainability and modern design, rarely mentioning that the fundamental architecture is a World War II military shelter. Some high-end architectural firms have rehabilitated the aesthetic, designing luxury versions with floor-to-ceiling glass end walls and premium finishes that cost $300 per square foot while maintaining the signature curved profile. The arch has gone from utilitarian necessity to design statement. Military applications never actually stopped. The U.S. Armed Forces still deploy arch-style shelters in conflict zones. Afghanistan, Iraq, and classified locations all feature modern descendants of the original Quonset. Current military specifications call for units that can be helicopter-lifted to mountain bases, assembled in combat conditions, and survive IED blast waves. The materials have evolved: aluminum alloy frames, Kevlar reinforced panels, climate control systems. But if you showed a 2025 military deployable shelter to the 1942 Quonset Point engineering team, they'd immediately recognize their own design philosophy. The recent innovation is expandable versions that deploy from shipping containers, unfold like origami, and lock into rigid arch structures within an hour. The economic argument that justified Quonset huts in 1942 remains compelling today. When disaster strikes or rapid deployment is required, conventional construction simply cannot compete on speed or cost. A modern engineered arch shelter delivers weather protection for approximately $50 per square foot, including shipping and assembly. Conventional construction in the same locations, assuming contractors are even available, costs $150 to $300 per square foot and requires months instead of days. For humanitarian organizations operating on donor funding or military logistics managing trillion-dollar budgets, this cost differential matters enormously. The math that drove Quonset development, how do you shelter the most people for the least money in the shortest time, hasn't changed because scarcity economics haven't changed. Perhaps the ultimate validation comes from space exploration, where NASA and private space companies designing Mars habitats keep arriving at Quonset-like solutions. Proposed Martian shelters feature arched profiles to resist the planet's severe dust storms, prefabricated components that ship on spacecraft, and self-supporting structures that don't require extensive foundation work in Martian regolith. The constraints of interplanetary construction, extreme environments, minimal tools, unskilled assembly, maximum strength from minimum materials, mirror the Pacific Theater challenges of 1942 so precisely that engineers independently rediscover the same solutions. When humans finally build permanent shelters on another planet, there's a reasonable chance those structures will owe their design heritage to 30 engineers working in a Rhode Island warehouse during the darkest days of World War II, solving an impossible problem with corrugated steel and brilliant simplicity.